singing will happen, happening, happen. Will happen, happening, happen, then will happen again and again, 'cause you and I will always be back then. You and I will always be back then. If there were some amazing force outside of time to take us back to where we were, and hang each moment up like pictures on the walls inside a billion tiny frames, so that we could see it all. It would look like will happen, happening, happen. Will happen, happening, happen, and there we are again and again, 'cause you and I will always be back then. You and I will always be back then. You and I will always be back then. That's why you and I will always be best friends. Hello, I'm Visnu. I play the ukulele, and I also like games, and so there's many things you might know about me or want to know about me. These are the things that are pertinent to this talk. I like games. I like lots of games, board games, card games, video games. Like a lot of you, I also program. And then lastly, I really like mischief. Because I think of it as a sounding board, jumping board, whatever that term is, into like creative problem solving, creative thinking, and innovation. I like mischief so much that I named my son Loki. This is my obligatory father shot of my son, who I'm so proud of. One of the games I've been playing is this game called Set. I was playing this game with my friend Susan. I want to kind of go over all the rules with you first. So it's a card game where, by the way, the New York Times has a set game that you can play. It's kind of fun, so you should go check that out. Set is a card game. It's a matching card game. You're trying to make sets of 3 cards each. All these cards have a color, number, pattern, and shape. I can toggle this on really quickly for any colorblind people. So amongst these attributes, what you're going for is a set of 3 cards where the attribute is either all the same or all different. And so here, this is an example of a set where the number is all different, 1, 2, and 3. The pattern is actually all the same. They're all striped. The shapes are all different, and the colors are all different. So this is a pretty fun game until you play with somebody like my friend Susan, who I want to give you a, oh no, I don't have music. I want music on my thing. Maybe there's music. Sound. Really quickly. That's correct. Let's try again. Oh, no music. So this is what playing Set against Susan is like. It's where she just starts taking cards, and I'm just observing and telling her, hey, good job. Wow, great take there. Almost had that one. Oh, okay. Wait, do I see something? No, not at all. So trust me, it is a fun game, but until you play against somebody like Susan. So how does that make me feel? As a protagonist of this talk, how does my protagonist dissatisfied with their life? I can't beat Susan at Set. What would it take for my protagonist, me, to find satisfaction? This is their goal, beat Susan at Set. What are my protagonist's biggest fears and character flaws? Well, probably 3 things. First is that I don't really want to put the effort into getting good at this game. So I could sit down and just play alone a lot until I get really good at this game, because it's tricking your brain into kind of seeing these sets as quickly as possible. But I am pretty lazy, and so not interested in that. I'm also impatient. I just don't want to take the time to do that. I'd rather use it to something else. And last of all, the mother of all character flaws, hubris. I'm pretty sure I was reading about StarCraft being beat by DeepMind and AlphaGo and AlphaZero, and I'm like, I can do this. I can solve set with my computer. And I can finally beat Susan this way. And so I started thinking about how this problem is formed. And so for a human, it's interesting because if you think of the problem in two parts, the set making is the hardest part for a human. When you can quickly see these cards and you know what they are, but you can't make the sets very quickly out of them. For a computer, it's actually the opposite. The set making is super easy, and it's the vision part that's the hard part. So as you can tell, we're going to computer vision the crap out of this problem. All right, here's the plan. I want this to run on my phone, so I'm going to use the camera on my phone, get into a browser, put it on the canvas, and then I get pixels. From those pixels, we're going to identify a bunch of cards in the thing. From there, we want to extract out every card. And then per each card, we want to identify the color, number, shading, and shape. And then eventually, we're just going to brute force and solve for the sets at the end. All right, so let's get into it. So this is my test image for this thing. As you can see, a bunch of cards. Getting them out. The things that you kind of care about are these ones. So this get image data is what we care about here. We get out this big, huge number array. So this looks kind of foreboding and creepy. It's got 11 million pixels in it. So let's go over what this image data object is really quickly. You can think of images as a series of pixels. Here we have 6 pixels, 6 huge pixels. And then each pixel is itself basically 4 numbers. There's a red, green, blue, and a transparency or alpha component, RGBA. So that's 4 numbers times 6 pixels. That's 24 numbers. So that's our 24 numbers that we see here. And then it's a flat array, so it's one-dimensional. But if you know the width, you know basically where to wrap it. And so this array corresponds to this picture up here. And if I change this, that's transparency, so that goes away. I can bring it back. I can make it black. I can make this one red. So you kind of see how those link up. So we're going to be using this image data object a lot throughout this talk, so got to get familiar with it. So first step is we want to threshold out. We want to simplify this picture a whole bunch. We're going to basically change it into straight black and white. And that's to make our jobs a lot easier later on. To do this, this is called thresholding. Ultimately, what I'm doing here is I'm converting every RGB value into a gray. And then if that gray is over or below a certain value, I either set it to white, 255, or black, 0. And so if I change this slider, you can kind of see how it affects the image. And then an entertaining thing to note here is that you'll notice that this is not a linear transform from RGB to gray. And that really quickly is, if you look at these green and blue values here, so this is actually the same amount of green and blue light hitting your eye, but because of how your retina is all jacked up, you perceive the green a lot more than the blue. And so you think green is a lot lighter than blue. And so that's taken into account with this formula here. All right, so we have a black and white image. Now we want to find those cards again. To do that, we go to NPM and just find some random package that finds contours for us. But what this package does, it's called more neighborhood tracing, which sounds scary because it has a dude's name on the front of it. And it uses neighborhood in the context that makes no sense whatsoever. But you can think of this as, say you're an ant, and you really like black pixels, and you're an exploratory ant. So you're just out for a walk, and you're maybe methodical, so you're just scanning through all this black. And then you all of a sudden hit this white pixel, and you're like, whoa, what is this? This is new. Let's figure this thing out. So you kind of back up, and you go to the side, and you try to hit it again. You're like, ooh, white pixel again. You back up, you go to the side. You do that a whole bunch until you're kind of like making your way around this whole thing until you're all the way back to the beginning again. And so if you've paid attention and like laid pebbles down, you've basically made and traced a path around this card. So that's more neighborhood tracing. You'll notice that I take the threshold image, run it through that. I get a bunch of contours. And then I end up filtering based on area here. And so if I kind of change some of these values, which now you'll notice that I'm twiddling values. A lot of these values have to do with the source image. So I'm kind of like picking numbers out of the air based on kind of the parameters of what I'm assuming. And that's going to be important later on. So here I've like made the area threshold go way lower so I can basically pull out smaller shapes. But I actually don't want those. So let's go back to here and only get 12 of them. So I'm back to my original 12 cards. And let's see, where are we? We want to now pull out each card. To do this, we need to simplify that path a little further. So that path is like a whole bunch of dots around that card. Ultimately, what I want is this rectangle-ish thing, or quadrilateral that consists of only 4 vertices. To do that, there's probably a cool name for this thing, but I made up some random way to do this. What I end up doing is basically removing pixels. So I want to remove redundant pixels along a line. And so I just keep removing it down until I'm down to 4. The way I choose which pixel to remove next is basically the one that results in the least area change, and which result in a pretty good rectangle at this point. Now I want to pull out every card. So this is now where I'm going from here to here. So this is called perspective transform, which again, you go to NPM, you just search for perspective transform, you get this thing. This is basically linear algebra. I'm not going to explain this one, but linear algebra, matrix math, you can pull out basically and transform from perspective into this perspective. All right, we got every card. That's kind of, so we need to correct for the lighting in the room, basically. You'll notice here that I took this in like a yellowish lidded room. Sometimes you get warm lighting, sometimes you get cool lighting. Ultimately, we want to kind of correct for that, so we want the background of the cards to basically be as like 255, 255, 255 white. To do that, we can assume that our white point, so we need a white point. We can assume that the background of the card is white. And so what I've done is just average the top and bottom borders of every card and call that my white point. And then using that, I can shift every pixel in the image in RGB space into basically where the background ends up averaging out to be more white than the rest of the card, and all the other colors end up slightly brightening also, which is actually good. Okay, so recapping where we are, we got our image, we identified some cards, we extracted the cards, and now we want to go for all of the colors and all the things in them. So here we have the spectrum of every card. So I've gone through and basically just grabbed every pixel, mapped it to a hue, and then thrown out all the white. So as you can tell, this is actually pretty indicative of kind of all the cards I ran through. And it's pretty easy to tell that there's a purple card, a red card, a green card. This weird one here is kind of interesting. So that one was actually this one here, where you can kind of see some rainbowing going on here, which is still fine. There's a lot of strong signal here still in the purple, so totally fine. Next one is number. So for number, again, I just throw contouring at it again. For each card, I run through the contour finder, and I get contours, and I end up looking at the percentage area, or sorry, the percentage width of the contours versus the entire card. So if there's one shape on there, it'll end up around 25%. When there's 2, it's around like 55%, and when there's 3, it's around 85%. And we can go ahead and correct for this kind of case where I miss a contour by just using this and mirroring it over here and assuming that, deducing basically that this is going to be 3. Okay, we got 2 things down. Next one's shading. For shading, we want to grab basically the inner core of every contour and look at its average luminosity. So to grab its inner core, you end up just taking a bounding box of the entire contour, cutting that down to like 3/4 of the size of the thing, and then averaging pixels again inside of that internal box to give you basically, so for an outline, you end up with white pretty much, so everything above 255. For striped, you end up with somewhere between 230 and 240, and then for solid, you end up with everything below like 180. Again, you'll notice that like I'm kind of like hard coding these values in at some point. Shape is a little bit more complicated. So shape, we can kind of do the same thing. Take that bounding box and look at the percentage area of the contour versus the shape. And then we get this. So a diamond is actually doesn't take up a lot of the area. Squiggle takes up a little bit more, and oval takes up the most. This, though, is getting a little close for me. So like this, the difference between oval and squiggle is a little iffy. So I decided to throw in yet another dimension here. So this is a convex hole. So this chart down here is the same as this top one, but I've added a y dimension, so it pulls out some of these values. A convex hole you can think of as like basically taking some saran wrap and wrapping these shapes in saran wrap, and so that's the shape you get. For oval and diamond, you end up with basically no change in the convex hull. And then for squiggle, you end up with more. So this pulls it out a little better and makes the classification a lot easier. Finally, we're down to like the brute force set finding. Here's where the computer actually has structured information in order to go ahead and look for all the sets. When you do the math, it's 12 cards, 3 cards per set. That's only 220 possible sets, which is absolutely nothing to a computer. It crushes this in 20 microseconds. And checking all of those 220 possible sets for sets. To kind of put this more into perspective, when you think of sets per minute, I'm at like 1 set per minute. Susan's good. She's at like 20 sets per minute. And the computer is at 300,000 sets per minute. So it's got us beat there by far. So then, knowing the sets, you just draw them back on the source image, and you got this cool looking thing here. So how does this play out? How did I do? So let's see. I'm going to give it away. But this is playing again against Susan with my first build or so. You know, I'm not doing so well still. Actually, there was no sets there. Oh, never mind. There was one. She took it. Oh, I got one. That's way better than I was doing before. And it was basically a pretty even match, actually. Basically, when Susan's slow, I can get a set. If she's fast, then I still lose. And that was actually due to, where's my slidey? Oh, no. How do I get out this way? So we lost in this example still. It was very sad. So what happens is that like we trained this thing on basically 1 or 2 or 3 source images, which is exactly the problem of overfitting. So I basically built the model based on like a couple source images. It didn't take into account a whole lot of different lighting that I might come into contact with, shadows, lots of other different things. And so the way to fix this is basically you get a lot of source images. So I went back and I built into my thing a way to quickly grab a lot of images and then tag them. And then based on that, I can actually try stuff. Or, sorry, I can train this a little better. So it's basically taking all those images and using those to inform all those magic numbers, which I call poor man's machine learning, which is exactly actually machine learning. So don't let anyone tell you otherwise. It's basically what machine learning is doing. So I put together a training montage. I don't know if this plays because it's on YouTube. Oh, it does. OK, hold on. I don't need sound. I'm going to do this live. Start over, because I got to time this right. Rising up, back on the street. Did my time, took my chances. Went the distance, now I'm back on my feet. Just a phone and my will to survive. So many times it happens too fast. You change your passion for glory. Don't lose your grip on the dreams of the past. You must fight just to keep them alive. It's the eye of the tiger, it's the thrill of the fight. Rising up to the challenge of our rival. And the last known survivor stalks their prey in the night as they're watching us all with the eye of the tiger. Eye of the tiger. Eye of the tiger. The eye of the tiger. All right. Oh no, that was I went out of full screen. No, full screen. Although all we're doing is a live demo next. Did I? Oh, I did. So could I get? So I have a plant in the audience, Anne. Everyone, welcome Anne. And then could I get a dealer? Is Miles around, or anybody who wants to deal some cards? Oh, a software update to my phone. Should I install this? Nah, let's wait. I guess quit iTunes that decided to open on me. Oh, look at some random images. Let's go to. So anyone who wants to cheat against their friends, go to set.visnup.com. And that is my screen. All right. All right. No dealer, huh? We need a dealer. A dealer would be great. Yeah. Ooh, Billy. Hi, Billy. I work with Billy. Can you?
4x4?
4x3?
4x3.
12? So, well, I have a chance of losing easily because the lighting up here is interesting. I tried this earlier, and I think I was okay. But also, Anna's pretty good at this game. And so we'll see. We'll see how this goes. Are we ready? Ready to go? Set. Oh, I'm cheating. I can take it because I'm a cheater. Oh no, these cards are weird. I gotta fix them. Oh, I gotta adjust some thresholding.
Oh man.
Is there anything here? Maybe? That's not one, that's a false positive. Oh, these cards are too close to each other. Wait for it. No, there's a set. One, here. This is where humans still have a chance, because computers can't see. Set. I think the pressure's getting to Anne. The stage pressure. Oh, there's an easy set. Yeah, go. Whoa, that was a harder set too. Yeah, set. Okay, I think we get the idea, because this is going to take a while to go through.
Okay.
But there's another set right there that Anne got. All right, I'm going to declare that a victory. Thank you again. So, great, we built something that works. I actually prepared for both versions of this. But we won, so that's good. This is a video just in case of showing that I also beat Susan. So I completed my accomplishment. So the remaining things I actually do here, so I did all of this in CPU in the browser. You could do all this in WebGL, which would be a lot of fun. This totally lends itself to shaders and GLSL. Given that I have this training set now, I can actually throw this to TensorFlow, which would also be a whole lot of fun. The other things I wanted to highlight really quickly are other versions of things that I've kind of built. Actually, I did not build medium snowflake thing, but so this is actually a totally different game. This is like a crazy game where you have crazy dice, you have figures, and you kind of build your character up over time. One thing about building your characters, you're going to have these item buys, and you're trying to figure out which of these is better, this DL44, this E11. They use random dice. They look the same. So I decided, I'm going to brute force this too. So I'm going to run simulations against all of this. And these are damage curves for each of these weapons at different distances. Another example that I want to highlight is actually this tool called Medium, or a tool called Snowflake from Medium. So this is actually a visualization of the engineering ladder. This is a little bit looser as far as actual tools to hack your life with. But to me, this is a tool that you can use to hack your career with. So you can kind of see where you sit on their ladder. For here, CRC is really good at project management and initiative and accomplishment. But she is very low on the community scale. She should probably stop killing people and blowing them up. But she can have a one-on-one with her manager, which I don't think she has a manager. And they can talk about how, she could probably target just doing this easy 0 to 1 on well-being and this 0 to 1 on community. And she's actually gone up a level. So this is just a tool that I feel like you can basically very quickly figure out if you've ever had a one-on-one with your manager and you're trying to figure out what's the next best thing for me to work on, what would happen if I just got really good at some of these other things, where would that put me? This answers it for you. So yeah, so again, why? I again love cheating and mischief and just solving problems in ways that shouldn't be solved. And I feel like it leads to basic innovation. So that's kind of why. I hope I've inspired you to actually build something and kind of shown that I've never done computer vision things before this, and this is my first pass at it. So I hope you can do that too. And then ultimately, all of these slides are on this website, Observable HQ, VisNup Cheat. That's me, VisNup. And there's actually blog post content inside of this. So if you share it, then it should make sense to all your friends too. Thank you.